Okay, here's the solution to problem number 1 from quiz from unit 2.1 on electrostatics, electric potential to be more specific. So we're given a problem where there's two identified charges, a positive 6 microcoulomb charge on the positive y-axis and a negative 9 microcoulomb charge located on the negative y-axis. Okay, so the first thing is to locate all the positions or all the points, aside from the trivial points located infinitely far away, where either the electric field is equal to 0 or where the electric potential is equal to 0. It turns out there's going to be 3 points we have to identify, and the answer is supposed to be in the form 0, comma, plus or minus y. The 0 is obvious here, right? These points are going to be located somewhere on the y-axis. There's not going to be any x value to these 3 special points we're looking for. And so to answer in this form avoids any ambiguity in the answer, right? Okay, so first things first, let's focus on where the electric field would be 0. So referring to this diagram, if this is a positive charge and this is a negative charge, then, gosh, if you try to imagine any point in between the two, the electric field due to the positive charge is going to point downward. The electric field due to the negative charge would also point downward. So there's no way you could get equilibrium in what I'll call region number 2. Now, could we have an equilibrium or a 0 electric field in region number 1? Let's see. Consider this point. Now the electric field from the positive charge is going to point up. The electric field from the negative charge is going to point down. Is it possible those two electric field vectors could be equal in value? Yeah, it is, because the vector that points up is closer to the weaker charge and farther from the larger value charge. So in fact, in that regard, we can rule out region 3, right? We're going to have electric field vectors in opposite directions. The positive charge is going to make a field vector that points down. The negative charge is going to make a field vector that points up. But the upward electric field vector will always be greater in magnitude than the downward one, so that wouldn't be equilibrium. Okay, so let's make a distance to this point in question and label it as d. Now, by the way, notice that d, the way I've defined it, is not a distance from the origin. So whatever we get for our final answer, we're going to have to add 10 centimeters to it. But in any case, I'm just going to say d is the distance from the 6 microcoulomb. So we already know this is 10 centimeters, so this whole distance here is d plus 10. Okay, and then the distance from the 9 microcoulomb charge is going to be d plus 20, right? Because this is also 10 centimeters. So how do we determine what's the value of this upward electric field? Well, that field is equal to k times, let's see, it's due to this charge, so we'll call it 6, divided by the distance is d. Okay, an electric field goes as an inverse squared law. So this downward electric field, we'll just say E up and E down. The electric field component points down is k times 9 divided by d plus 20 quantity squared. Now you might say that should be a negative 9, not a positive 9. No, I've dealt with the fact that it's a negative charge by drawing the electric field vector in the downward direction. All I'm really going to say then at this point is the magnitudes of these electric fields are equal. And when I set them equal to each other, the k cancels out. And also, you might have said, wait, isn't it microcoulombs, not coulombs? It is, but this would have been times 10 to the negative 6. This would also be times 10 to the negative 6. And of course, those would cancel once I set these equal to each other. So for that to be the position where the net electric field is 0, it has to be true that 6 over d squared is equal to 9 over d plus 20 quantity squared. If we cross multiply, we get d plus 20 over d all squared is equal to 9 over 6, otherwise known as 1.5. If we take the square root of both sides, d plus 20 is equal to rad 1.5d. So d is equal to 20 divided by rad 1.5 minus 1, which gives us 89. So then what's the distance from the origin? Remember, I have to add 10 centimeters to that. So the value of y would be positive 99 centimeters. So we say E equals 0 at the point 0, comma, positive 99 centimeters. Boy, that's just the first part of A, stating where the electric field is equal to 0. Now, where would the electric potential be equal to 0? Well, we know the electric potential is equal to 0 infinitely far away, unless otherwise stated, right? Now, in total, the net amount of charge for this system is negative, more negative charge than we have positive charge. So let's see, I'll say that instead of considering this the x-axis of position, I'll say that this is the axis for potential energy. We'll say positive this way and negative this way. So we know electric potential is negative near negative charges and positive near positive charges. So the electric potential, again, if I extend the y-axis, it's 0 here. So if I'm making a graph, the electric potential, oh, I shouldn't call this U, I should call it V, right? In other words, it's U over Q. So the electric potential is getting more and more negative the closer we get to this net amount of negative charge. And in fact, it's at its most negative value at the position of this negative charge. And then it comes up in value. Over here, the electric potential gets, again, more and more negative as we get closer to this overall net negative charge. But at some point, we know close to the positive charge, the electric potential has to be positive. Okay, so somehow our graph of electric potential versus position on the y-axis might look like this. So it looks like there's 1, 2 points where the electric potential is equal to 0. And by the way, right here, the slope of this graph is equal to 0. Of course, the slope is also 0 here and here, but those are trivial points because we're just saying that inside of the charge, the electric field is equal to 0. So this point where the slope is 0 is this same point we found here where the electric field is equal to 0. Okay, so we're going to take the same approach here. Let me call this distance d. Now, electric potential is a scalar quantity, not a vector quantity. So I want to come up with an expression that says the net electric potential at this point P is equal to 0. So the electric potential can be found based on the superposition principle. Some of the electric potential at that point is due to the positive charge, some of it is due to the negative charge. So the amount of electric potential at this point P due to the positive charge would be K times 6 divided by D. Not D squared, right? Electric potential is just equal to KQ over R. Okay, and in addition to it, there's an electric potential from the negative charge equal to K times negative 9 divided by D plus 20. Now this time, I can't ignore the fact that it's a negative value when I plug it into the equation, because I'm not just simply setting magnitudes in opposite directions equal. I'm trying to find a net value based on the superposition principle. So hopefully this all adds up to equal 0, meaning I can divide both sides of the equation by k and cancel it out. So this means 6 over d is equal to 9 over d plus 20. D plus 20 over d is equal to 1.5. So d is equal to 20 divided by 1.5 minus 1, which gives us 40 centimeters. But remember, I'm going to have to add 10 centimeters to that. This is the distance from this charge, but I want the distance from the origin. So I have to add this 10 centimeters. So at the point 0, comma, positive 50 centimeters, v is equal to 0. Okay, so that's one of the places. Now we got to find this place where the electric potential is equal to 0. So let's continue to use d as a way to represent the distance from the 6 microcoulomb charge. Okay, so this time we have k times 6 over d plus, now the distance between these two is 20 centimeters, right? So if I'm calling d the distance below the positive charge, then this distance right here would be 20 minus d. So plus k times negative 9 over 20 minus d. So the only difference between this expression, well, wait, let me take one more step. All this has to equal 0. This is the net potential. So I'm going to add 9 over 20 minus d to both sides of the equation. So 6 over d equals 9 over 20 minus d. So I want you to compare this expression with this expression. The only difference is the plus sign became a negative sign, right? 20 minus d over d is equal to 9 over 6. So again, this value of 1.5. And so we get d is equal to 20 over 1.5 plus 1 instead of 1.5 minus 1. So in this case, we get d is equal to 20 divided by 2.5. Yeah, 8, right? But that's the distance from the positive 6 microcoulomb charge, where we want the distance from the origin, so that must be 2 centimeters. So there it is. We have our other position where the electric potential is equal to 0 at 0, comma, positive 2 centimeters. Okay, so the bulk of our work in this quiz problem was in this part A, locating all these special points. I won't promise you, but I think these next 3 problems will go a little faster. For sure, part B is a pretty simple one. What's the electrostatic potential energy of the 2-charge system? Well, potential energy is K Q1 Q2 over R. So it's 9 times 10 to the 9th times 6 times 10 to the negative 6th times negative 9 times 10 to the negative 6th divided by 0.2. Grab your calculators, and hopefully you'll agree that this comes out to negative 2.43 joules. Of course, I've left the units out. I'll leave it up to you to convince yourself that these units combine to give us joules. Part C. How much work is required to move a negative 2.5 microcoulomb charge from this point to the origin? Okay, well, I'm going to work based off of the idea that or I'm going to find the solution based off this idea that work is equal to the amount of charge you move multiplied by the difference in electric potential between the 2 points it's being moved from. So the point that it starts at, we're told, is 10 centimeters, comma 0, and the point we're going to move it to is the origin. So if we can find the electric potential at point 1 and then find the electric potential at point 2, V2 minus V1 would be this difference in electric potential, and this Q is given to us as negative 2.5 microcoulombs. Okay, so I guess I have to do these two steps. Find what's the electric potential at the origin and find what's the electric potential at this position. Well, from the symmetry, the distance from our positive charge to this point is the same as our distance from the negative charge to that point. And if this is 10 centimeters and this is 10 centimeters, then this distance here, which I'll call d, is 10 rad 2. So finding the electric potential at this point number 1 is based on the superposition principle. It's K times 6 times 10 to the negative 6 divided by 0.10 times rad 2. I want to get it in meters, not centimeters. And then also K times negative 9 times 10 to the negative 6, also divided by 0.10 times rad 2. So I can factor out the K and the 0.1 rad 2. So 9 times 10 to the 9th divided by 0.1 rad 2, and then simply times, oh, and well, I guess I could also factor out the 10 to the negative 6th. When I combine that with 10 to the positive 9th, this becomes 10 to the 3rd. And then 6 added with negative 9 is just negative 3. So this all comes out to negative 1.91 times 10 to the 5th volts. That's the value of the electric potential at point 1. Now at position 2, the electric potential is, well, it's almost the same thing, it's just our distance isn't 10 rad 2, our distance is just 10. So it's going to be K over 0.1 without this rad 2 times 6 times 10 to the negative 6 plus negative 9 times 10 to the negative 6. So again, K is 9 times 10 to the 9th. I can factor out the 10 to the negative 6, so change that to 10 to the 3rd. 6 combined with negative 9 is negative 3. So this is 9,000 times negative 3 divided by 0.1. We don't need a calculator for this one, right? That would be 270,000, or negative 270,000. In other words, negative 2.7 times 10 to the 5th. So the difference between these two values, delta V, is equal to V2 minus V1, which gives us a value of negative 79,081 volts. So the work is equal to Q times delta V. We have a negative charge being moved through a negative difference in electric potential. And the product of these two values gives us very nearly 0.2 joules. If you want a lot of sig figs in your answer, I think it's 0.1977, but 0.2 will suffice. Okay, so we've got our answers to A, B, and C. Now we need to get the answer to part D. What's the net electric flux through an imaginary sphere centered at the origin, well, let's see, the distance here is 10 centimeters. So if we've got a sphere of this radius, all I know is it's a big enough sphere that encloses both of those charges. So what's the net electric flux? Well, the hard way to do this would be to say net flux through that enclosed surface is the vector dot product of EdA. That would give us the net amount of flux, right? That's the hard way to do it. The easy way to do it is to consider another thing that this is equal to. Well, by Gauss's law, this is just equal to the amount of charge that lies inside of that surface divided by epsilon naught. Well, the charge inside of the surface is a net charge of -3 microcoulombs. So -3 times 10 to the -6 coulombs divided by epsilon naught. Let's see, that's 8.85 times 10 to the -12th, right? So this comes out to -3.39 times 10 to the 5th Newton meter squared per coulomb. Or you can think of it as newtons per coulomb multiplied by square meters, right? Field strength multiplied by area. All right, thanks for watching.